This is only by video, but what can you do? Okay. So, hello, hi. So, okay. It's still early, right? So we have to wait. But anyway, it's working. So this is good sign.
Yes,
okay.
Yes.
This is a very good sign. Okay, great. Fantastic.
Wait for a few more minutes.
Yeah, sure. I'm fine. I wait and see how it goes. Okay?
Thank you.
Yeah, thanks.
Sure. With pleasure.
Chandan, please put the YouTube on. Chandan, are you there?
Sir, it's working. Just refresh your page, please.
Okay.
Mhm.
Hello, everybody. This is Ujjwal Sen from HRI. A very good afternoon. Today, we have Professor Zeilinger with us. Professor Anton Zeilinger is working at the Institute for Quantum Optics and Quantum Information in Vienna and the University of Vienna. There is no need to introduce Professor Zeilinger to this audience. Let me just say that his contributions to quantum information science in particular and science in general help us even in the very language we speak in. One example being the G8Z state. And let me stop keeping the audience in further hold and request Professor Zeilinger to begin his keynote talk. Professor Zeilinger.
Okay. Let me just launch. Hi, everybody. I'm sorry that this is only by video, but what can we do in these times? I hope all this passes away soon. Can you hear me?
Yes, yes, we hear you.
Okay. Can you see my screen? No, not yet, right? Hello?
Hello.
Can you hear my I have to share my screen with you guys.
Exactly, exactly.
Here we go. Now, does it work?
Yes.
You see my screen?
Yes, we see your screen. You have to make it full screen.
All right, let's do that. No, it's not full screen yet. These things are able to do too many things. That's the problem. Let's see how it goes. Calling again. I join the meeting. I see myself here. Okay. I see the list of participants, but not you guys. Wait a minute. How can I? But not the screen. Let's see how it goes. Here is the. So, do you see the screen now?
We see, yeah, now we see. Yes, yes. But it's not full screen.
It's not full screen. Maybe this way?
Yeah, yes, I think that's the one.
This way?
It hasn't yet come. Yes, yes, yes. It's perfect. It's perfect.
It seems to be slow. Anyway, okay. So, all right. So this is a talk for 45 minutes. Or what's the story?
Yes, exactly. There is 45 minutes the talk, and then there are discussions about 15 minutes. These are, of course, approximate.
Okay, great. Okay, so I just want to give you, thank you for the invitation. I just want to give you in the beginning a small overview of how things developed over the years. Actually, what you see here is a telescope, evidently, but it's the optical ground station on the island of Tenerife in Spain. And we use it for optical ground station to communicate optically with satellites. We use it, here you see a laser, we use it for testing quantum communication to another island and also for connecting with satellites, most notably the Chinese satellite Mitzius. Here to set the stage of what the time scale is. And as you all know, quantum physics began in the 1900s, early 1900s, by people like Planck and most notably Einstein. Einstein was probably the first person who realized that quantum mechanics implies some really new view of the world. Then very soon a debate started where Bohr and Einstein were most notable participants about what the theory means. And by that we do not mean what it means in terms of experiments. You know, we have the quantum state, and using the quantum state, we can perfectly make expectation values and future results and so on and so on. But in a sense, what was pointed out by Einstein, also by Bohr and others, particularly the behavior of individual quanta is strange in a sense, offers some fundamental puzzles. And it took until the 1970s when such fundamental experiments became possible. We were lucky to do some of these early experiments with neutrons and later on with other particles. But to the surprise of everyone, in the 1990s, people invented new concepts for quantum information, like quantum computer, communication, teleportation, and so on. And this slide I wrote about 5 years ago, so I'm not changing it. About 5 years ago, I predicted that around 2020 we have the start of the age of quantum information with the quantum internet and so on. And this is actually coming through now with some experiments in various countries. But let me go to the fundamental issues. This is a famous picture by Feynman in his Feynman lectures on physics. He shows an electron gun, but it could be anything else which produces particles, and they are passing through slits. And when you have one of the two open, you see when slit one open, you see the probability distribution P1. When the other is open, you see P2. And when you open both, you don't see the sum of the two, but this kind of interference pattern, which is easily understood, as we all know, if you attribute waves to what is passing through the slits. But if you talk about individual particles and what they do, interesting questions came up. And actually here Einstein in 1909 made one of his few mistakes. He said that for individual particles, there should not be a double-slit interference pattern. Here is a picture from the Bohr-Einstein dialogue written up by Bohr, and I recommend to everyone to read this paper, the Bohr-Einstein dialogue written by Niels Bohr. It's really about the fundamental issues of quantum mechanics. Now, if you talk about individual particles, then Einstein says, how should a particle passing through, say, slit 1 know whether slit 2 is open or not? It can't. Einstein's words in simple ways is it can only know that if there are more particles and they meet each other and they can carry together the information about whether 1 or 2 is open. Now, here Einstein was wrong. And the modern view is the old view is that if you would try to find out which slit the particle passes through, you would impart enough momentum such that the interference pattern is destroyed. The modern view is that interference occurs if and only if no path information is present anywhere in the universe, be it on the particle or be it somewhere else, which of the two slits the particle passes through. And this is a new role of information which is not present in classical physics. Now, and the important point now is that it is the possibility to obtain knowledge about the past. It doesn't matter whether an observer actually takes note of that information. It's enough that this knowledge could be obtained by any observer with sufficient technological means. And there already interesting consequences start, which the early people did not know, namely that when this information is present in the universe, you can erase it. You can destroy the information, and if you do this in an irrecoverable way, then you regain information. This is the concept of quantum eraser, of which I will talk in a little bit later on. Here's a picture already quite some time old, which we took with fullerenes, with these buckyballs, these famous carbon 60 or carbon 70 molecules. The interesting part here is that even this large molecule is delocalized. It's delocalized in the sense that its quantum state passes through the two slits. It would be wrong to say that the particle passes two slits. This would obviously be nonsense, and because there's no way to make sense out of such a statement. But anyway, the question is, how far can it go? And this research is going on now. It's a vigorous line of research going to nanoparticles and so on and so on. And there's no fundamental limit. It's just a question of, in principle, ingenuity. I know that this is a very, very courageous statement, but there are hundreds and thousands of years ahead for us for developing this kind of thing. Experiment. So superposition, which we just saw, is one of the fundamental issues. The next fundamental issues is the random noise. I just show you a semi-reflecting beam splitter here, and we have some light impinging on it. Half of it is reflected, the other half goes through. Then we know from quantum mechanics, if you take individual particles, replace the laser by a single photon source, then we know that the state is in a superposition of both possibilities. Then which of the detector fires is completely random? And there's nothing in physics which allows us to answer the question where it goes up. So this complete randomness is also something new, which does not exist in classical physics. And it bothers many people, like the famous John Bell, who discovered his Bell inequalities, which show that a local realistic viewpoint of the world cannot be upheld. He demanded that physics has to explain why events, namely individual events, happen. And this cannot be the case. This is outside of present physics. It would require a major change of current mathematics. So therefore, it's extremely unlikely. Anyway, this is the first possibility how to obtain a quantum bit, a qubit, a specific qubit here, which, as you all know, is central to the quantum information technology. Einstein was uncomfortable about this randomness, and he said that in any case, I'm convinced that God does not play dice. In a famous letter to Max Born in December 1926. This letter exists in the internet in a very good English translation, and I would also suggest you to read it, because it's very deep, even as Einstein was not always right. The third point, which is fundamentally important for our understanding in a conceptual way, is, besides superposition and randomness, entanglement. The fact that two particles, here symbolized for the fun by a pair of dice, are connected in a way that each of the observations on the two is completely random, but they are perfectly correlated. And Einstein said, Schrödinger in 1935 already said that this is really the characteristic trait of quantum mechanics, which forces us to depart from our classical lines of thinking. Unfortunately, he did not tell us what the new lines of thinking would be. Just a quotation, to show you how the field developed, we are talking about. This is the paper by Einstein, Podolsky, and Rosa and Roten in 1935 about this quantum locality. Sorry, I have to take a sip because I have a little bit problem with my throat. I hope it's not anything serious, but who knows? Now, this paper came out in 1935, and you see the interest really only started in the 70s, just out of mathematical or the intellectual curiosity. And in the 2000s, it really exploded. And this was when entanglement and other fundamental concepts started to become important to fundamental physics. Here is a short picture of what goes on in a Bell inequality experiment. You have a source. This is German word for source, which creates entangled particles, and you measure the polarizations on the two sides, which is now it's a straightforward and very simple technique. In the early experiments in the 1970s by Friedman and Clauser, and then by Aspe and his group, it was a non-trivial question how to measure the polarization of individual photons. But now it's standard. You can buy all this. And it turns out that there are perfect correlations between the results on both sides. The individual events are random, and you cannot explain the correlations you obtain by just using properties of each particle on its own and including properties of the measurement apparatus. This is the famous conflict of quantum mechanics with local realistic properties, and there have been a lot of experiments which all follow this scheme I show here: a source and two measurements, one on each side. I don't want to go into this historic details anymore. I just present you some recent development. The point is if I may go back here, the experimentalist decides what to measure on particle A and on particle B. Okay. I want to make my picture smaller, so okay. So I see better the screen. Okay, A and B. And then the results come out. Plus or zero, you can call it plus or minus, it doesn't matter. These are just names. An important point is if you want to make sure that this side doesn't influence the other side in any possible way and vice versa. So you have to separate them well in space, you have to use quick switches, but on the other hand, you also have to make sure that the decision here is completely independent. Now, in decisions by two experimentalists, now it could in principle be that something unknown influences in the common past influences the two particles. And this can be some unknown physics, something which we don't know yet. And physicists, we should be also always open for the new, for the unexpected. Now, there was a proposal by three American colleagues. Sorry, I didn't write. Yeah, it's PRL 2013, Galicia, Friedman, and Kaiser, who said, well, if you do this kind of experiment and make a measurement on this particle here, this one here, then here we decide which polarization is being measured. For example, if we take polarized photons or whatever, then we want to take randomness, which is as widely separated in space as possible, and as far out as possible, because any common cause must have happened very early in the universe. And this is by looking at two quasars, quasar 1 and quasar 2, which are as far out as possible, and then you might be lucky and have no common source, very, very small. Such an experiment we did in 2018, where we have a source here. We send the two photons over free space links. This was on the Canary Island of La Palma. Source is inside here in this container over here. Then we have two telescopes. These are two telescopes of about 4 meter diameter, which is a decent sized telescope. It is the only location on Earth where two telescopes of this size are so conveniently separated from each other. This looks at one quasar, this looks at another quasar, and then by taking fluctuations in the color of the light from the quasars, you decide, based on the fluctuations, you decide whether Bob measures the photons in this basis, horizontal, vertical, or 45 degrees, and Alice measures them at this basis, which is rotated by 22.5 degrees from this. And then you look at the correlations, and lo and behold, you find a violation of Bell's inequality. Now, the future of such experiments, any common cause in this kind of experiment is about, roughly speaking, about 1 billion light years after the Big Bang. So it's quite long ago, even before maybe, sure, but the numbers we can look up. Now you can go further back by making future experiments with the cosmic microwave background, or you can go even further back by looking at neutrinos directly from the Big Bang, which should in principle possible, but is far out of current technology. This I don't show. Here's the next point I want to talk about is a specific application of entanglement, quantum teleportation, where you have, what you do is you have a quantum state, this one here, which can be any superposition of a qubit in any possible superposition, 0 and 1. This can be polarization states if you want, they can be frequency states, they can be momentum states, you name it. You want to teleport this state over to Bob. Here, Alice wants to teleport. And what they do, as you probably know, if you have had an introduction to modern quantum experiments, Alice and Bob share an entangled pair. Entangled pair in this state, for example, 0, 0 plus 1, 1. And then Alice projects these two onto an entangled state. There's a Bell state measurement, as it is called, Bell state measurement on entangled states. There are 4 possible results. And depending on what result you get here, this photon is projected onto a well-defined state, which contains all the original information from the original state, alpha and beta. But it can be hidden. Here's the mathematical expression. What you obtain, here are the 4 different entangled states, 4 different states for the teleported photon. And depending on this result here, you have to perform a rotation on that state to obtain the final, the original here. The point here is that this feature protects relativity theory from being violated by this experiment because the information about the correct rotation can only be transported with the speed of light. Now, the most interesting situation, which is conceptually most interesting, is the teleportation of entanglement itself, which was already pointed out in the early theory papers by the original proposers, Bennett et al., and so on. The point is that you have an EPR source, you have an entangled source here, an entangled source here. And now clearly there is no, these are independent sources, so clearly there's no correlation whatsoever between photons, for example, emerging here and emerging here. They are from independent sources, they're completely independent. But then the point now is to project 1 photon each from these 2 sources onto an entangled state. This can most simply be done using a beam splitter, a 50-50 beam splitter, which if you obtain coincidences here, 1 photon here, 1 photon here, then you don't know whether this photon came from here or there. You don't know whether this photon came from here or there. You only know that they came from different sources because of the property of the beam splitter, which means that you entangle these 2, and therefore you also entangle the outermost one. This is conceptually quite interesting. Here's the the way how a beam splitter operates, but this is for any 45-degree rotation or 90 degrees, depending what basis you choose, in a two-state system. The point is, when the states have this kind of shape, 1, 0 plus 0, 1 of the two photons, you have two photons incident on a beam splitter, 1, 0 plus 1. Again, this can be polarization, horizontal, vertical, or you name it. Plus 0, 1, then what can happen is that the two photons can either be transmitted by the semi-reflecting mirror or both be reflected. And if this is a state of the symmetry, then the two possibilities extinguish each other, symbolized here by 0. So if you look at the coincidences between the two detectors as a function of time difference, we have some coincidences in the beginning and they drop to 0 when the time difference vanishes. This is the famous Hongo-Mendel dip. But what is important in our experiment is the opposite. Namely, if you have an antisymmetric state, 1, 0, minus 0, 1, which can happen when you project randomly on one of the bases, then you have the fact that the two possibilities extinguish each other, meaning that they enforce each other before they extinguish each other. Now they enforce each other that before, sorry, maybe my wording wasn't correct. The both possibilities are 0, therefore the two photons come either out here or they come out here. So this I didn't say. In this case, they enforce each other, which means that the two photons, sorry, this is my dog. The two photons are always coming out, one here and one here. So if you take a beam splitter, you get one photon out here, one photon out here, then you know that you projected on an entangled state. And this is a workhorse in many of our experiments. Very simple. Here you see the results of a certain number of random coincidences, but when the time difference is 0, you get the maximum. Now comes an important fundamental issue, which was pointed out by Asher Perez, a famous Israeli physicist who unfortunately passed away already in 2001. He said the following. Suppose I have one source here and I have one source here. Okay. They produce each one an entangled pair. If I want, I can project these two on an entangled state. In that case, the outer two ones become entangled. Or on the other hand, I can also measure the polarizations of these two photons separately, in which case these are not correlated. So you can decide, so you register the result, but you can register the result earlier before you do the decision whether you project on an entangled state or not. Now, this means that the later decision decides whether the two photons here were entangled or they were not entangled. These are two mutually exclusive properties, so both cannot be the case. And Perez pointed out that this is quite interesting, because it shows that the quantum state is not something given. It is it is a statement about the full experimental situation. Now, now combine this with the famous delayed choice Gedanken experiment by Wheeler, where he said, if I have an interferometer here, semi-reflecting beam splitter, waves coming in here, and then I can decide at a later time whether I insert the beam splitter or not. If I insert the beam splitter, then I get interference pattern. I don't know which paths the particles took. If I don't insert the beam splitter, then I can find out what path it took. And I can make this at a very last moment. So the property, whether you have a wave propagating on both things, or whether you can talk about the particle, is something which is not decided in the beginning of the experiment. Here's a famous picture, but I don't want to go into these details. Here's an interesting result on this delayed choice entanglement swapping experiment, which we did some time ago, but I mention it here because it points out the really fundamental issues. You create two entangled pairs, one here, by the same pump. And then you detect measure one photon, Alice measures his one photon's polarization here, Bob measures his photon's polarization here. And the two other photons are delayed by glass fibers, and they are then sent through an interferometer here. You see interferometer here? And the point is, which is quite important, that you can set the phase of this internal phase of the interferometer such that each of the outgoing beam is a superposition of the two incoming ones. In that case, you project this onto an entangled state, or the phase is such that this one always comes out here, and this one always comes out here. So you measure the path. The results show these are the correlations in three mutually unbiased spaces: horizontal, vertical, right, left, and plus minus, which is plus 45 degrees, minus 45 degrees linear rotated compared to that. If entanglement swapping works, then these two results, which are these, should be correlated in any basis, which is the case here. If it is not entangled, if there's no entanglement swapping, they should not be correlated. So this, to me, this kind of experiment shows that events are more fundamental than quantum states. I just see that the time is flying, and no, let me just show some how the technological progress makes things possible. This is a long distance experiments between teleportation between the Canary Islands of La Palma and Tenerife, and here entanglement swapping between the two islands of La Palma and Tenerife. Now I want to see, because time flies, I want to see what else I would like to discuss with you here. Time is okay, all right. So we are in good shape actually. It's not so bad. We go on here. That's the experimental setup results. I don't have to show that. We can go on here. A rather recent experiment is this one here. Teleportation of qubits of quantum of three-state systems, not qubits, but three-state systems, which have state 0, 1, or 2, or whatever. And the idea is a very similar one, but it's quite an involved experiment. This was done in cooperation with our friends in China. You created a three-state system to be teleported, and the new idea is that you have to use ancillar photons. You have to create. You have to use actually, besides the three-state entangled systems, you have to use additional ancillar photons, which you send in and throw in a bucket. This is quite interesting. And then the teleportation of qubits works. Why are these experiments interesting? Because as you certainly know, teleportation is viewed as a way how future quantum computers could talk to each other over long distance. And if you can teleport qubits, then you can teleport more information than just with qubits. Now I want to come to another fundamental point. You might know this basic experiment here, performed by Wang, Zhu, and Mandel in the 1990s. What you do is you have a source, a laser, which pumps two nonlinear crystals and creates an entangled pair here and an entangled pair here. And the question now is, is if you superimpose, for example, this could be different colors. This could actually be green and red. If you superimpose these two photons on a beam splitter here, do you get interference, yes or no? And the answer must be no, because the other photon can be used to find out from which source the particle came. So you have path information, and you cannot have path information at the same time as the interference pattern. But if you look at coincidences, a detector here, then in both cases you erase the information where the particle came from. This could have come from here or here. This could have come from here or here, and therefore in the coincidences you get interferences. Now there is an experiment, a further step, which Greenberger, Horn, and myself in an old article called mind-boggling, and that's the idea of having two nonlinear crystals, each one creating the pair. Is only one pair here, only one pair. Like before, there was also only one pair in a superposition of both possibilities. Okay, here's one pair, either created here or created here. Now the point is, you again superpose two modes from one crystal and from the other crystal, from the other medium, onto the beam splitter. And in principle, you should not get interference, because the other beam, this one, if you get the photon here, you can find out whether the pair come from here. If you measure the photon here, you can find out that the pair come from here. But the idea was actually by Wu, and the experiment was performed, sorry, there we go. The experiment was performed then by Su, Wang, and Mandel. If you send in this mode such that it completely overlaps with the mode created here, then there's no experiment you can do to find out whether the photon pair came from here or there, and you get interference. So it is the mere fact that by overlapping these things, you make information inaccessible, which creates interference. That is a step beyond the quantum eraser, where you have to erase the information. Here, the information does not even exist. This is quite interesting. It's the old experiment. We use this kind of experiment in quantum imaging with undetected photons, where you create pairs of photons. In this crystal here, in one crystal, you create a pair, and here you create another pair, and that you imagine is the path between the two pairs. And you can put objects into this beam and image them over here using the other photon, even as the light which passes the object never is detected. This is very important. The light that passes the object is never detected. So using that, you can have phase imaging, you can have absorption imaging, you name it, all kinds of different possibilities. Such a scheme is actually important, and I mentioned technology in my title. In that way, you can make images, for example, of biologically sensitive material, where the light which you use in the detector would destroy the sample. And when single photon detectors do not exist for all wavelengths, and it can very well be that you have to use a much softer radiation to investigate the sample than what you use for detecting the image. And that's a program which is now followed by various groups. It would be a direct application of quantum information of this non-detecting scheme. Interesting point is also maybe that there is a interesting enlargement. You can use different wavelengths here in the object. You can use a different wavelengths than here. And there's an interesting enlargement possible because of this feature. Here is one more. These are different objects which were shown, but I don't want to go into details anymore. Now, the continuation of these schemes has led to a new idea, which we called entanglement by path identity. I would like to, I say here, this is another success of Melvin. I should mention on the side, Melvin is a computer program developed mainly by Mario Kren, my former student, which is to design, maybe I show you the program in the, maybe I have it here somewhere. Let me see. Let me see. I may have, yeah, I may have something here. Here is something. There is a, but it will come in a moment. I go on here, which can design quantum experiments. I will mention the point in a moment again. And what you do here is you take various crystals, sources which produce pairs. They don't need to be entangled. They can be product pairs. And then you send the modes back into other crystals like here, and you look at the fourfold coincidences. And that way you can create multi-particle states with much higher efficiency than with any other possible schemes. Here's a rendering of possible multi-particle systems and so on, which this is a field which is just in the beginning of being developed. Now, Mr. Chairman, you kindly mentioned the Greenberger Zeilinger experiment, so I have to show you some more recent results here. The point is to show these correlations beyond quantum bits, beyond qubits. Here is this is a GHZ state for qubits. So 3 photons are either, or 3 particles are either in the state 000 or 111. And then it can be seen that there are stronger violations than with 2 particles. And also this kind of states has become important in error correction schemes, in quantum computation, in quantum secret sharing protocols, and you name it. Now the question is now to go to states where you have 3 particles, but also 3 states for each particle. So this is a step beyond what I talked about before. More particles and more states. Now clearly this would have an increased information capacity. There are new error correction possibilities, and so on and so on. Now, how to do it? With a qubit GHZ states, you can, for example, and this we did years ago. Jian Pan was my student on this experiment. We have pairs. We create pairs, and we use a polarizing beam splitter. Okay, the polarizing beam splitter has the property that the vertical photon is reflected, the horizontally polarized is passed through. So it can easily be shown that if you then detect 4-fold coincidences, which means you create 2 pairs here, 1 photon here, 1 here, 1 here, 1 here, then these are in a GHZ state, actually in a 4-particle GHZ state. That means if you look at possible correlations between the 2 sources, you can have a direct correlation between HAH and HAH on both sides, but you also can have diagonal situations. These are removed by the polarizing beam splitter. Now, in a higher entangled state, this is not so simple. If you would insert any kind of device which is similar to a polarizing beam splitter, you could get additional terms. Without going into too much detail, the question was how to find a solution. And there, the computer program Melvin came into place. what we basically do is we give the computer program a toolbox with various setups. The setups can be improved, the computer program can learn, and so on. And then we ask, what is the simplest setup you can invent? Now, for these GHG's cases, we use what's called orbital angular momentum states. So if a photon, besides the standard spin angular momentum, which is +1 and -1, along or antiparallel to the propagation direction, it can also have this kind of screw type phase front, which means that the photon can carry multiples of h bar angular momenta. So here are photos of these pictures taken at various modes. This is a mode with L equals 0, so it's a standard wave, which you know. This is L equals +1, so one unit of angular momentum per photon. Here 2 units, here -1, and so on and so on. I pass this. Now the solution is extremely complicated, which was invented by Melvin. It involves, this is the analog to the beam splitter here, which we had before. It's a multiport with 3 inputs, 3 outputs, and quite an elaborate machinery inside. Why I don't want to go into details here, but I just want to give you the message that this can be done in experiments. Again, here's Melvin's solution, but maybe I shouldn't go into details here. The results confirm the expected density matrix, which you need for this kind of 3x3 state. Now, I mentioned already, by the same schemes, we did teleportation of 3-dimensional photon states, and it's clear that this is an interesting road to go on in the future. Now, I think I have used up my 45 minutes. Here is finally Wikipedia, where Schrödinger is wanted like the Schrödinger cat, not dead or alive, but dead or alive. Thank you very much for your attention.
Thank you, Professor Zeilinger, for this very illuminating talk. And now, with your permission, I will ask the audience for some questions.
Professor, this is Shomukanti Bose.
Yes, yes.
I have 2 questions. Probably I missed that part. One is regarding the bosonic and the fermionic example that you took, phi plus or psi plus, and the Hongu-Mandel experiment. In one case, at the 0 delay, there was a dip, and in other case, there was a peak. What is,
Yeah.
I mean, I probably could not follow that. What is the reason behind it?
Okay, let me try to go back. Share screen. Here we go. No, does it share it? No, I don't. Wait a minute. I should start the PowerPoint presentation. No, I have it here. I have it here. I try to share the screen. Here we go. Yep, here we go. Do you see the screen now?
Yes, yes.
Okay, perfect. So let's go back here. Now here's the
19 or 20, I think. 19 and 20, slide number.
Yeah, I'm here already at 19. At 19. I'm 19. Can you see it?
Yeah, I can see.
Okay, very good. So what you have is you create a pair of say photons in this state. 1, 0 plus 0, 1, where say 1 is horizontal polarization, 0 is vertical polarization and horizontal polarization. So it means that these 2 modes here have different polarization, but it is not defined which is horizontal, which is vertical. Okay, so then you send these 2 onto a beam splitter. Okay. And then what can happen, for example, is that either both photons are reflected or are passing through, or both photons are reflected or not shown here. That, for example, this photon is reflected, this one goes through, okay? Or this photon is reflected and this one goes through, okay? These are also possibilities. Now, it turns out that sorry, these are fermionic. I go back to the bosonic state. It turns out for this kind of state, these two possibilities extinguish each other. Why? The reason is that in any beam splitter, or in a standard kind of beam splitter, a reflected beam picks up a phase of pi/2. A reflected beam at the beam splitter, this is a consequence of the unitarity of the evolution. Picks up a phase of pi/2 and here a phase of pi/2. So this situation, the total state of the two photons picks up a phase of pi. Phase of pi means that it has exactly the minus sign in front of the state compared to the state. Therefore, the two extinguish each other. Okay. Now, for the other state, you have already a minus here.
Oh, okay. Yeah.
The additional minus upon the two reflections, you get a plus and you get coherent superposition. Okay?
Okay. Okay. And the other question is regarding that this quantum optical imaging, where you used two different setup. One is from the Hong and Mandel, and another the other one, where just let me get over this optical imaging. Two nonlinear optical amplifier, two in.
Here's one of them.
Yeah. That one.
Here's one of them. What you do here is standard two photon interference in a way that you have two pairs. If you have one pair created either here or here. Okay. And then you superpose it's only one pair, so it's only one photon in these two beams.
Okay.
So you superpose the two modes on a 50-50 beam splitter. You would expect, because this looks more or less like an interferometer here, that you get interference. But the answer is you don't get interference because the other photon could be used. You put a detector here and one here. If this detector clicks, then you know that the green photon was created here. If this detector clicks, you know that the green photon. If this detector clicks, you know that the green photon was created here. So you could use the other one to find out where this green photon was created, and therefore you can find out path information, which is illegal. You cannot have path information interference at the same time. Only if you do the same with the second photon, you also superpose it, you also detect it, then you erase the path information completely, and you get interference. Now, the new thing here in this scheme is, maybe I show another picture. This is maybe more instructive. You have the two crystals. Each one creates a pair. This creates a pair, this creates a pair. And again, you have a beam splitter here, and you ask yourself, do I get interference? Now, the new idea of Zhu, Wang, and Mendel was that if you arrange these crystals, because they are transparent in such a way that the light mode coming in here completely overlaps, coming from the first crystal, completely overlaps with the light mode created by the second crystal, then there's no experiment whatsoever possible on this one to find out whether the photon came from here or here. So you have no path information, and therefore you get interference. So you get interference without detecting the other photon. This is really the new part. You can do a lot of experiments now with on entanglement. This is entangled. On entanglement without detecting both photons.
Okay.
Hello. And there is a question from YouTube by Anindita Bera. The question is, recently entanglement swapping with photons has been, entanglement swapping has been shown with quantum dots. Can you shed light on that? What will be the percentage of swapping for fidelities?
I know about these experiments, quantum dots, and the basic point is that they use instead of nonlinear crystals, they use quantum dots to create pairs. And the big challenge in quantum dots always was to have them identical enough such that the photon pairs created here the two photon pairs, this one and this one, is indistinguishable by their properties. So they have, the same polarization, the same mode structure, the same frequency in both crystals, and so on. The big challenge in quantum dots is to produce them in such a nice way that that photon pair created from this one and from this dot are undistinguishable. And then you can do this kind of entanglement swapping experiments and so on. Okay?
Thank you. There is a question by Ribhu Gupta. He asks, increase in number of parties and number of states per party enhances error correction capacity. But does it also increase the errors involved? Is there a competition between the correction capabilities and the errors incurred?
This is actually a very good question. I don't know of any fundamental theoretical investigation of this, which could be my fault. I don't know. There's certainly an increase in error probability, which as experimentalist I can certainly confirm. The higher dimensions you have and the more particles you have, the harder it is to achieve the corresponding the necessary fidelities. What exactly the spin-off between both are is a very good question, and I would like to know if anyone else has a quantitative answer.
Thank you. The next question is by Arun Poti. He asks, when you say events are more fundamental than quantum states, is there any formal way to obtain quantum state from events?
That's a very good question. I want to formal ways is I don't know what that would entail. I would like to quote here Niels Bohr, who at some point said that the quantum state is a representation of our knowledge, which we obtain on the basis of what we know about the apparatus and on certain observed events. Okay, so the events in that case are a fundamental thing how to go. The connection between events and quantum state has to do with the information carrying capacity of any system. And there are some interesting connections, but I don't think that this is a kind of fulfilled research program in a sense.
But to have an event, we also need the quantum state. So right.
No.
So we have some quantum state and we do some measurement on the quantum state, and then we get some event. So I don't know how to really, how to connect or how to say that event is more fundamental than quantum state. So
well, I know that the statement is very difficult to grasp, because for many physicists the quantum states are kind of the most basic thing. Now, if you just look at this experiment, you obtain a measurement result here.
Yeah.
You obtain a measurement result here. And there is no way to associate the quantum state to the situation yet. So you can only do that after this other measurement. So the measurement result is there and sort of cannot be fully interpreted.
But when you do this measurement at this stage, unlike polarization measurement, you do that on a quantum state, right?
Well, that's a good question. That's do we
So
do it?
there is something behind. I mean, there is something, you know, in back of your mind that there is something on which you're doing this measurement, and that has a quantum state, right? So
I agree. There's a photon there. Okay.
yeah.
Let's say we get a detector click, and with some probability from earlier knowledge of the sources, we can say what kind of polarization comes out, right?
Mm-hmm.
But I would not use words like the quantum state is responsible for what kind of measurement result we get.
Mm-hmm.
This is, I mean, this is a big question. The quantum, what is the quantum state itself? Is it a representation of our knowledge, of our information,
Mm-hmm.
or is it something out there, existing, you know, in its own?
But what is your you know, your deep thought, or you know, your view about having a fundamental notion about events, and then from that you emerge, you know, or the quantum state emerge as a, you know, as a
I had
or something, you know. So
I had difficulties understanding you now. Sorry. Can you repeat? I did not understand you acoustically.
no, so I want to know. I mean, do you have a clear? I mean, do you really believe that measurements or events are more fundamental, and somehow quantum states should emerge from that?
I think this is this is a challenge.
Yeah, right.
It's a challenge I put out, right? My personal belief is yes, but I could be wrong. I mean, I could, right?
Okay.
I could be wrong. Would not be the first time that I'm wrong.
Okay, thank you. Yeah.
Would you take a few more questions?
Well, I'm getting a problem with my throat now slowly, but maybe one more question or so.
Okay. So the next question is by Devdut Sharma, and he asks the concept of quantum imaging through undetected photon, as mentioned by you, and the quantum ghost imaging concept given by Pittman et al. In 1995. What is the difference between the two concepts?
That is a very good and important question. There is a significant difference, and I pointed out here. Let me show the thing. If I look, well, I don't have a good. Well, let me use a good picture of entanglement. Let's see where I have where do I have an entangled state here? Here we go. For example, here we go. Here we go. So if you have an entangled source, the idea of ghost imaging is that you put an object here, make a detection of the photon passing through the object. And if you do this right, if you project on the right superposition here, then you get the image on the other side. Okay? You can get so you can detect the ghost, so to speak. But you always have to detect this photon here. You always have to detect the radiation going through the object. Now, in our new scheme, this is not necessary. If I just show you the new scheme, like here, you have this green and the red light. You can obtain the image back there, and you put the object into this beam. Now, this beam just passes through. It doesn't do anything, and you don't have to detect it anymore. And that is the new thing, which distinguishes it from the ghost imaging idea.
Thank you. So, I mean, there are still a few more questions, but I think in the because your throat is not feeling well, I think we stop here.
Thank you.
Thank you. It was splendid to have you with us today in the evening.
It
Thank
was
you.
nice. It was nice
Okay,
meeting you.
okay, thanks.
I wish you all the best.
Thank you.
Thanks.
Thank you very much.
Okay, bye-bye.
Yeah, bye.
Bye. Bye.
Picture.
Ah, I forgot about the picture. You should have told, right?
I told you, I messaged you privately.
Yeah, that is true, but you should have messaged to everybody. Then everybody would have remembered. I forgot completely.
Okay, maybe
Did he
we'll
leave
stop.
already? Oh,
Huh?
he left, no?
No, we can at least have whoever is
there was a question by Shivashish Ghosh and another by Sumit Mukherjee, but I could not because he
I
said.
think, yeah, because he said his throat is not well, so I think we should stop. But maybe we can take the picture of us, whoever is now online.
You can Photoshop Zeilinger later.
We can superimpose Zeilinger's picture.
Actually, I have taken some picture which I can superimpose. Yes.
We have to take his permission before that.
No, that we can do. So can everybody make their video on and we can take a group picture?
I think we put off the YouTube now and
Yes.
free Chandan.
Okay, sir, I'm doing.
Yeah, so
Maybe you can also join in the picture because
you put the YouTube off,
You
join us in the picture and leave.
also stop the recording. Chandan, you stop recording now.
Yeah, we are doing it.
Okay, so everybody is where is Sharonath? Why he is not?
And who is taking the picture? Ganesh again.